let's recall some stuff that you already have seen. And this is more just a notational thing. Whenever you learn a language, you should probably know what the letters and symbols mean. So now we're using curly Ds. And this is where notation is going to matter, especially with the chain rule, because we're going to start mixing regular derivatives with partial derivatives. And if you don't get the that curvy D versus a regular English D, then it can sometimes get confusing. So if we're taking a partial derivative, our function varies with x and y, say. If we're doing it with x, if we want to evaluate it at a specific point a, b, this is one way you could denote that. This is, I don't really like that notation because it's a little bit unclear. This is far more common in the textbook and also in general, is they'll do the df dx, then they'll use the evaluation bar with the point. So this is preferred to this, but if you do see this, it just means this. And another way you could write this is just with the more streamlined notation, fx evaluated at ab. I like this the most because it's efficient. And I also do lots of LaTeX. And so and having something linear instead of a fraction is always nice. This works the same way for y, right? So if this was a function of x and y, then we can do it with y now. If we want to evaluate it at the point AB, again, you could write that as df y evaluated at AB, or just fy now, if we're going to differentiate with the other variable evaluated at the point. So take your pick. My personal preference for efficiency and for clarity, this can be helpful in certain problem applications when you're trying to show your work. This is kind of disgusting, but if you choose it, it's technically right. And that's all personal opinion. So as long as you know what the symbols mean, you're good. Let's run through some examples just to get our brains warmed up. So if I have a function that takes two variables, x and y, that I've got x cubed minus y squared plus 4, then there's two partial derivatives I can take, right? I can take fx, and that's how you can say that with words, fx, where this is the partial derivative of f with respect to x. And here, everything is a constant except for the stuff that's x's. So here we get 3x squared. But then that's a constant, so 0, constant, 0. And then fy, constant, 0, minus 2y, constant, 0. And that's all there is to it. So here's another one. Let's have a function fxy sine x times y. So the xy is the argument of sine. So if we take fx, so the derivative of sine is just what? Yeah, so it's cosine. So the rule is cosine. So we'll have cosine xy. But then we have a chain rule, right? So x is the variable, y is just a constant. Right? So it's constant times our variable, chain rule is going to be a y. And then fy, you'll notice there's symmetry in thought here. So derivative of sine in general is cosine, right? Cosine. And then we have the argument xy. Now we do the chain rule. The constant now is x because y is the variable. So that constant multiple. So there will be symmetry like that, or at least some pattern, especially with trigonometric chain rules and such. Cool. Let's do one more. That's a little bit more complicated than it involved. We can incorporate other derivative rules like product rule. So we could do g of xy is equal to x squared times e to the xy. Okay, so we have a function times a function, no? And so we'll use the product rule. So if I want to find gx, I'll do left d right plus right d left. So left d right. So we have exy, because that's the rule for exponential, but then chain rule, y is constant. Okay, so multiply by the number y. So that is left d right. Now let's do right d left. Derivative of the left with respect to x is just 2x. And then we copy this over. And we can make this look less horrible. This is just xe to the xy multiplied by xy plus 2. That would be how you would want to represent the partial derivative of g with respect to x, or just gx. And then gy is actually going to be easier. You're going to see why in a second, because there's no y's in this function over here. So that means this entire thing is like a constant. So left d right, we have left d right derivative. That's the same thing. Now, instead of it being the y, that's the number that gets thrown down. What's going to come down? Yeah, the x. And then right d left. Well, what's d left?
What?
Yeah, 0. So 0 times whatever that's going to be 0. So we're done. And you could obviously simplify it because that's kind of horrible to leave x squared and then x. So x cubed dx. So these partial derivatives, just know how to do your regular derivative rules, and you got it. I'll supply you a practice example on your own. And I like to call this a diagnostic. If you can do this, you're good. If you can't, keep at it until you're able to do this comfortably. So here's, I'm not going to go over this in class, but everybody write this down. fxy is equal to sine x squared y in the arguments of sine here, times the natural log square root of xy. So it's just a basic derivative, and then find fx and f. So do that on your own time. If you can, if you look at that, you're like, I can do that. If you sit down with the paper, sit down, I can do that, then you've got the skill that you need for the rest of this class in partial derivatives. Okay. I'll leave that up here. I'll erase this stuff. And I'll give you, I guess, a heads up now. A lot of people will drop off kind of conceptually, or they'll get behind, and because chapters 15 and 16 are so long, just chronologically too, in the calendar. So I'm thinking there's going to probably be a chapter 15 quiz. Just so that you stay sharp on chapter 15 stuff before you dive into all the integrals. Because then with the pattern I notice is that we get to exam review for both chapters 15 and 16, and ain't nobody remember how to take a derivative. And so then it's just like, well, we got to go back, you know, not just to square one, we got to go back to square 0. Like you somehow managed to make one of those. What did I write? For real. Okay.
He wrote ONG.
So here's a notational thing that is going to get some people, especially people like me, because I am dyslexic. So this kind of stuff is important to clarify. We can have higher order partial derivative. So in the same way that you can take in Calc 1 f prime and then f prime prime, f prime prime prime, and then f to n primes, right? You can take as many derivatives as you want. We can do the same thing with these partials. We just have to be more careful about what we mean by notation. So here's the notation that you might see. In my opinion, this is the ugly version. So it's where you're going to differentiate partially with x the partial derivative of your function that's already been differentiated with respect to x. And if you do that, so you have your partial with respect to x, but then that's what you're differentiating again. It's like doing x twice. Then that could be written, we notate that d squared f over dx squared like that. Here's kind of what I prefer is what's happening is you're taking, because this is more streamlined notation, you're taking fx, and then that you're doing with respect to x again. And so really this is fx. So instead of denoting primes up here, we're now just listing out the variables that we differentiated with. Now notice, well, you can't see it here. We will see it in a second. Let's do the other uniform one. So d dy of df dy is d squared f dy squared. And that's the same thing, more streamlined. We take fy, right? So this is fy, and then we're differentiating that with respect to y. And then we get fyy. This is used for f of x and fyy. This notation is used far more in the textbook than the d squared f dx squared, etc. So get more familiar with this. This is more useful. Here's where it starts to get a little goofy. So d dx, because now if you think, wait, hold on, there's two variables. Can't I mix them, right? What if I do the x first and then the y second or something like that? So here, we're going to do y first. So we're going to differentiate with respect to y first. Then after we do that, then we're going to differentiate x second. The way we denote that in this notation is d squared f over dx dy. Now, the only reason I don't really like this is because it's misleading. Most of us read English and left to right. And then, so you would think, oh, I must have done the x first and then the y second. That's not right. Because this notation is just taking the fact that you did the, this is like Greek word order versus the English word order. So that's why I like this notation better, because it's going to be more clear what's going on. If I wanted to take fy and differentiate it with respect to x, then the way you write it out is exactly how you would think about it in English. F, do y first, then x. Whereas this one is kind of like, okay, hold on a second. The x is here first, but what really happened was it's because it's the outside thing of y, which means the y would have had to go first, and then we do x. If you like that one, then that's okay. Just know that this is going to be more intuitive if you are used to reading left to left, understanding like that. So this indicates the order that you're taking the derivatives in. So in the other way, it's going to be d dy, and then df dx. So this is saying now do the function first with x, then y second. Then we have the kind of confusing notation where we kind of reverse that order and we say y dx, even though we really mean to say differentiate the x first, then the y. So that's why I like this notation, where we just say it straightforward. We have fx, differentiate with respect to x, then do it with y. And then that's just fxy. So I know exactly what order, reading that left to right, we did the derivatives. And then that's all the combinations, right? Now, if you were to have a function that had more variables, you could obviously keep going. But this is just establishing all of the different kind of combinations for the language of these mixed partial derivatives. Okay, so thumbs up. That's clear. Raise your hand if you're team this. Good. Raise your hand if you're team this. All right, fun. That means I'll be able to read all of your labs much easier. Okay, let's run through an example now. And let's do what? Yeah, this is one that you're gonna, oh, I could erase that. This was up for making sure you know how to do that one. Oh, I mean, we got to figure it out, right? Okay, so f of x and y is equal to 3x to the fourth times y minus 2xy plus 5xy cubed. Okay, let's go through all four of these. So we're going to do our building blocks. The building block is going to be fx and fy. And from there, we can build everything else. So the easy stuff is fx, which is going to be 12 from the power of x cubed, y is hanging along because it's a number now, minus 2y, because y is a number with the 2, and x is the variable, plus, now, don't think that we assimilate the y cubed. We're not doing a power rule here with that, because this is just a number. 5y cubed is just a number, x is the variable, so 5y cubed. And then at y, now all the x's are constants. So here's the variable. So we have the constant 3x to the fourth. And then here's our variable again with the constant multiple minus 2x. And now we can use the y cubed because now this is the function. So 3 times the 5 is 15. X, because that's a constant, y reduced the y power by 1. So these are the kind of ingredients. Now we have fxx, fyy, fyx, and fxy. So fxx is going to be taking, okay, let's take fx. And what are we going to do to this one?
Second, take the next derivative. of
Yes, with respect to which variable?
X.
Yes, we're gonna differentiate this one with respect to x again. So here, 12, we got the 3 dropping down, so 36. X squared, the y is still chilling because we're differentiating with the x. Now that is
Minus
what?
Zero.
And that's gonna go to,
0.
yeah, so that's it.
Oh.
And then fyy, which one of these two are we gonna look at for this?
We want Fy.
Yeah, right, fy. Now that we're locked onto fy, do we differentiate again with x or y?
Y.
Right, so that tells you which one and then how to do it again. So
That was is
that's gonna turn into what?
0,
That's gonna turn into,
0.
now this is the only thing that has y in it, so it's
30
y,
30
so
X.
it'd be 30
X,
x and then the y,
Y.
because you decrease the y power by 1. Okay, was that good? So the difference between fxx and fyy.
Yeah.
Okay, now we can do the mixed partials here. So let's do yx. So out loud, what's the order of differentiation going to be?
Y first, and then X.
So which of these two, top or bottom, am I going to use to start?
Fy.
Yeah, fy. Now I have fy. Am I going to do it with respect to x or with y? Okay, so now we accommodate these x's, right? So this is just 12x cubed, and that's just minus 2. And now here, let's see. Yes, 15y. Because x is the only variable contained. And then fxy. Okay, so what's the order of derivatives here?
X. And Y.
Okay, so we'll start with fx. And once we start with fx, we'll differentiate this with respect to which variable.
Y.
Good. So here's the y. So that 12x cubed is acting like that constant most well-round. Now, minus 2, what's the derivative of minus 2y with respect to y? And then what's that going to be?
What's this other thing?
What, bitch?
Mic drop.
Okay. What do we notice here? Oh my goodness, is that always going to be the case? Mike's got the right answer. I sure hope so. Now, this is the reason I use this example is because it's going to motivate the next theorem. In other words, instead of just showing you the theorem and you'd be like, I don't care. You'll see this and you're like, oh, okay, it's an explanation for why we have this. Okay, so let's take a look at Claral.
I'm just using them.
How much of what?
I was gonna mark it.
Oh.
How much?
So here's our theorem. I'd write this one down. Claral. I just probably insulted every single like French person who speaks the language. Okay. Equality of mixed partial derivatives. Mixed partial derivatives. First things first, we get our terminology straight. Is it intuitively clear that if it's fyx or fxy, this is what we mean by a mixed partial derivative? Because it's mixed. Okay. This is going to say, let f be defined on an open set D on an open set D of R2. We're gonna let fxy and fyx be continuous. We don't want them to be discontinuous. So continuous in D. So they don't have to be continuous for every single possible y and x combination, just in our open region here that we're talking about.
Is that a computer sign or?
This
No, rather like the overall.
Yes.
By the R.
R2,
Yeah, it's R squared.
R2. So this is like reals. It's like think of the plane.
Oh.
Yeah. if those conditions are satisfied, then fxy indeed will correspond with fyx for all, a reminder of what that symbol means, for all the points xy in our region. Do you see why I like math? Because this saves me the space of having to write out the phrase for every single point xy in D contained in R2. It's a very dense language. It's very pretty. Okay, so basically this is no fluke. We're dealing with polynomials. Polynomials are continuous on all the reals, which means that regardless of any really region we take in R2, it's not going to change anything. We're still going to be have the continuity. So we have continuity in our region D, whatever that might be. In this case, the domain, we can just take all the reals, so R2. So they will correspond for all points in our region, which happens to be for all of R2. So that means this doesn't actually always work. You could have a mixed partial that suddenly breaks continuity or something in a specific region that you're looking at. And in that case, you can't necessarily assert this. But I think for the most part in this class, we just deal with the nice case. Okay. 128. I'm going to show you this in passing because it's really not that important in this class, but I'll look at what differentiability is. And really the concepts of the differentiability are just little echoes from what you already did in Calc 1. So I won't spend too much time on it because the chain rule is far more important to you guys' GPAs than this. Now, if you raise your hand if you're pure mathematics. Okay, so there you go. We're gonna, you'll need to see the definitions if you paid for the class, but we're not gonna dwell on this for an entire lecture. We could spend an entire class talking about this definition if we wanted to. But that's not what we're here to do. So Z is fxy is differentiable at some point A, B, provided. Then there's a whole laundry list of things that we need to do. Fx at AB and Fy at AB exist. As I write this out, pair every single condition with the analogous condition from Calc 1. So we have the function, the derivatives existing, and the change delta z, which is f of a nudged over some delta x, and then b nudged over some delta y. If this can be written equal to, and then we have to subtract from the original point. If this can be described as fx ab delta x plus fy at ab delta y, and then we have to accommodate for the leftovers that can occur. So epsilon 1 delta x and epsilon 2 delta y, where for fixed AB, so once we fix what A and B are supposed to be, epsilon 1 and epsilon 2 are functions that depend totally on the delta x and delta y, with a limiting condition where as these epsilons, epsilon 1, epsilon 2, going to 0, so those are getting smaller as our nudges in the x y approaches nothing. So infinitesimally precise. So then a function is differentiable on an open set R if it is differentiable at every point in Y. It's a lot of words. Okay. Here, I'm gonna highlight what you need to take out of this. Calc 1, let's recall. We would say that if I had y is equal to some function, then y prime is equal to f prime x. Or we could say that dy dx is equal to f prime x. And so what we would do is we started describing this notion of a differential as dy being f prime of x dx, right? In other words, an approximation of this infinitesimally precise thing could be an approximation. If we take some nudge in y, that's the rate and a nudge of x. And then at a specific point in time, so some x equals a, we would have a nudge, the slope at that point a, and the nudge. This is just a construction of a change of the function value. Nothing's changed. We have that nudge, that's analogous to that. And then we have a rate at a point, and I'll put this in dotted. Rate at a point, that's analogous. And then we have the nudge in the variable. That's in the variable. Now, we happen to have more variables here, so we'll do that in every single direction, right? We'll take our slope at the point and our nudge for that direction, the slope of the point, and then the nudge in that direction. But it's all analogous to what the differential is brought back. Now, we do certain things with this. The theory behind it, you might go, why on earth does this exist? I don't have time today to do the derivation. If you're ever curious, you have a textbook that goes over the derivation. But lecture time is too precious to spend on that. We gotta get to the chain rule. So is this good? I'll just add a few little notes here. This is a lot. That's a large definition. So the main takeaway is this. Differentiability implies continuity. That's it. This has not changed since Calc 1. Differentiability implies continuity. Now I ask you, is the converse true? The converse would flip the order of these things. So now what you're saying is, does continuity imply differentiability? No, we all know that's not true. So it's not going to suddenly change for surfaces. And then the other result is knowing that if you have your partial derivatives being continuous containing your point, and then you'll have differentiability for f. But this is really the main one. So from this kind of definition, take away the structure of how the change in z is formed with respect to what we understand it to be in Calc 1. You understand that, and then also differentiability implies continuity. That's the main meat of this matter. The other things are more tedious details that aren't really necessary for future concepts. All right, you feeling good? We can do the fun part of the lecture now. The chain rule. It's pretty fun. It would have been more fun if we would have proved it, but the slightly different context. On one of these days, instead of doing a regular lecture, I'll just walk you through the proof of this problem that I solved for a journal article. And then we can do a quiz on that instead. You guys like music?
Yes.
Any specific genres you guys like? Swing, yeah.
Like product music.
Okay.
Yeah, really?
I just love, this is a good class because of all the genres, we had a diverse array of genres and nobody said country, and that's a good class. Okay, so here's the theorem. There are different ways we can construct this. And this will, in some form or another, be on the exam, almost guaranteed. Chain rule. And then we're gonna first do this with one independent variable. We'll increase the number of variables. We'll start with just one independent variable. Okay, so here's how this is gonna work. We're gonna have some function that it's gonna be f. Now, normally I would just put x and y. But on top of having x and y, I want each of those to actually be functions of something else. So x is a function of t. Y is a function of t. And x and y are themselves variables for this function. Okay. So here's kind of how this works. So the z, this is dependent. So the z is the dependent variable. Why is it dependent? Well, because it gets no say. It is whatever gets spit out. Now, well, what's the difference between the x and the y and say the t? So the x and the y are what we call intermediate. They're intermediate variables because they're not the fundamental parameter that governs this entire function. But they are functioning as variables inside of, they're being represented as variables in the function. And so then t all the way down to that single variable, this is the true independent variable. So t is independent here. X, y are intermediate between the independent and ultimately the dependent variable is set. So if I refer, I'll be using this language. Figured I'd give you the little key here so that you know what's going on. And so how do we do, if I wanted to say, okay, I want the derivative of z with respect to this parameter t. Notice that these are regular d's, not curvy. The reason for that is because there's only one variable. There's no need for a partial derivative here because we're going straight from z with respect to that one variable t. And that's the only variable, it's one independent variable. So here's how we're gonna do it. They take turns. So we need to accommodate the x stuff and we need to accommodate the y stuff. So let's first start with the x. We partially did, we gotta go z through x. So we're accommodating our function starting with x. And then from x, we need to get to t. But notice that we can actually just do dx dt as a regular derivative. Dx dt. Regular, partial, regular. But we're not done because we're ignoring our y, so we can't do that. So we've got to add. We do the same thing. So we start from z. Now we go down, we turn down the road y's direction. Once we get into y, now we need to do y to get to t.
Wait, the first dt, that's regular.
All right, what?
The first d dz dt, is that regular?
Yes, this is the regular derivative. Because it only has one variable. And then dy dt. Here's why this notation exists. It's because it makes building these really easy. That's intuitive. So I'm trying to cancel the, I'm trying to get at the end of the day, something with z, something with t in the bottom. So if I start down the road of z to x, I need to end up that. So switching, and you get dz dt. Both. Okay. So let's make sure we actually understand this idea. And let's extend it. Extend the idea. So now if I have some function w, I'm defining it as x of t, y of t, z of t. I want everyone on their own paper to write what regular dw dt should be. Write out the chain rule formula, mimicking the pattern here. Everyone gets turned from w and sourced all the way down to t. And I'll draw a little picture. give me a thumbs up when you've got it on your page. Okay, now if you're still working on it, follow me through this picture. So we might be more visual learners. Here's W, the big guy. Big guy's got 3 kids. And each one of these have a toy. So when you create this, each one of these arrows that shows you the relationship is representing derivative. So from W to Z, because, so first of all, how many variables is W taking? Right, so the answer is it's more than one, so that means we got to be doing partials. So from here to here, that's going to be a partial derivative with respect to x. And then this little guy going from W to Y is going to be the partial of W to Y. And then this in this direction is the partial of W to Z. Okay, cool. And then now, but how many variables is x depending on? Right, so there's no need for a partial. So from here to here, it's actually just a regular dx dt. Now what about from y to t? Okay. Regular dy dt. How many variables is z taken care of? One, so no partial derivatives, just dz dt. So when you create this chain rule, what you're really doing is you're accommodating for every single string of these to the root. So we follow the first one. Let's go down this route. It's going to encompass here, to here, to here. So that we're going to chain together dw, going down the x root first, and then x follows with t regular. Okay, now following that same kind of pathway logic, how do we get from w through y to d?
dw, dy. dy dt.
And then the last one?
dw dz. dz dt.
Very good. Find a way for yourself to distinguish between partials and regulars. Because that supercell goes pretty crazy if you get a bunch of stuff going on there. So this is again, remember when I said be picky about your notation? Now it's gonna matter. You're gonna look, if you accidentally put this as a partial, you just fundamentally misunderstand the concept. Then if you do a straight instead of partial, so if you made this regular dw dx, well, you've missed the whole idea that w depends on 3 instead of just 1. So that's a good litmus test to be able to know, do I know really inherently the structure of my function that I've been given? Now, do we necessarily restrict our function to only having 3 like x, y, and z? No, it could have 40 for all I care, and you throw it into a computer and it'll all the way down. Now, here's the next question. Do we necessarily have to depend on only one independent variable? No, we can have more. So let's take a look at how to build the chain rule for that. Actually, okay, I'll pull the class. Do you want to see an example of doing the one independent variable? Like, do you want to see a computation done, or do you want to go to the next? Okay, raise your hand if you want to see the computation. I'm raising a bunch of abstract things. That's great. I was like, do I have to? It was more just an excuse that I didn't want to have to remember my unit circle for the example. So, Lloyd and inconvenience to be like, oh yeah, that's right. I'm still supposed to know what that is. What is sine of pi fourths, guys?
Sine of pi fourths.
What's tangent of 3 pi fourths?
3 pi over 4.
Whoever said 1, good.
1.
No, it'd be negative 1.
Negative 1.
Because you're in the second quadrant for that.
I always have to do this in my head.
Yeah, no, there's whenever I did exams with unit circle computations, I'd be sitting there with my arm, like,
remember.
ching, 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 figuring out where everything is
I
at.
remember I was in trade and it was COVID. It
All
was
right,
like
so this
from
is
the
going to be Tangle. Tangle.
So hopefully I'll have a unit circle. Come on,
It's going to be two independent variables, or I'll just say more. In the independent variable. Now we can have as many things as we want. It's like a little family tree that we can make here. So suppose we have then, and our function takes x and y. But here's how we're going to do it. Now x is going to have its own little kids here, s and t, and y is going to have s and t. All right. So this would be like you, and x and y are your kids, and then eventually your kids grow up and they have their own kids. Yes, s and t. So these are that's
Wait, so is the S's kid the T?
well, no, because s and t are
No.
siblings. They're the independent
weird.
variable.
Okay.
So if you really think about this, what are the okay? Let's actually identify this. So now we have the language. Tell me what is the dependent? Which one's dependent? Good. That one is that. What is the intermediate?
X and Y.
X and Y. And what is the independent?
S and T.
Good. Which means that this function isn't just changing with respect to one independent variable. There's two independent things doing their own thing, and then that's going to spit out different values. It's a more complicated, but it's a more sophisticated model. Okay, now fundamentally, that means, is it possible to have a regular derivative z to any of these variables?
No, it has to be partial.
There's more than one variable in every single one of these circumstances. So if we were to draw this tree out, we're looking at the kind of like the parent variable, the dependent variable, the big problem. Yes. So x and y. So z is responsible for x and y in this scenario. And so how many variables is it? Is it taking care of more than one?
Yes.
Yeah, so we use partials. So it would be dz, dx, and dz, dy. Now, before it was easy because x was only responsible for one variable, so we could do a regular derivative. But now what's happening
It's partial.
is it's responsible for f and t's independent variable. S and t. And so can I do a regular derivative anymore?
Nope.
Oh, it's going to be now partial x, partial s on this side, and partial x, partial t on this side. And then over here, what's going to be from the y to the s? What's that going to be?
Partial Y.
Good. And then over here,
Partial Y, partial T.
there you go. Now you can build this chain rule by just taking every single path. Yes.
So would the overall notation be partial z to partial s to partial, or would it be the direction?
Good question. How many independent variables is z ultimately rely on? Yeah, that's more than one. So in the same way that if in the very basic sense, if I just said fxy, automatically the notion of only having a direct derivative doesn't even exist because we're just like, but there's two variables, you got to accommodate for them. So here you could really think of z as actually just being a function of only the s's and the t's. You really wanted to think about it that way. And so there's no such notion now as just a direct derivative from z to any one of the single because there's no longer a single independent. So what you would say then is there's two things we got to find a formula to. Do we care about the s side of the fan or do we care about the t side? And either way, you can still follow both tracks in both ways. You just generate two formulas. So if I have, let's get the formula for dz down to the first independent variable s. So notice that this has to be partial. So even though this is describing the formula for the chain rule, it has to be partial because I have more than one variable. And so we follow the track, right? So going down from z all the way to all of the s's on this side, I have to use this So I need to go from Z and get to X. And then from X, I use X to get to S. You guys see that visually and also visually. There's a visual here and the visual in the way that you set theta. Very, very fun to do. Okay, so then what's the next one gonna be?
dz dy.
Actually, let's make a rule for the class. D is gonna be reserved for a regular derivative. If you say partial, I'll know that you mean the curve ED.
Okay.
Cool, okay. So what's this one gonna be?
Partial y, partial s.
Wait, hold on.
Partial
It's not
z,
only
partial
yeah.
y.
Gotta start from the top. So partial Z, partial Y, and then what's after partial Z, partial Y?
Partial y, partial s.
Good. So this is the formula for doing a chain rule. So I want to go from Z to specifically this one of the two possible independent. But there are two possible independent variables, so I need two formulas. So I have partial Z now wanting to get down to partial T, the other independent variable. Okay, so what's the first combination going to be here?
Partial z, partial x,
And then what's after that?
partial x, partial t.
X. And then now we accommodate the other side of the family. So we get
Partial z, partial y.
so 154. Here will be your exit ticket. Okay. Here is a function w, and it's going to be f of x, and x is going to be depending on p, q, and r. Y is going to depend on p, q, and r, and z is going to depend on p, q, and r. So that means how many total partial derivatives from w are we to have? Yeah, 3, because how many independent variables are there? 3. Yeah, there are 3. So we would need to find partial w, partial p. We would need partial w, partial q, and a formula for partial w, partial r. All 3 of these need a formula, and you can get those with the intermediate variable. So this is your exit ticket, and then you are free to go.